If we remind ourselves about the underlying population, because in this case, we are aware of the whole population, there is actually an 8-year difference between the men and the women. My sample was a 9-year difference, so that's a pretty close approximation to the truth, to the real difference. Our visual reasoning skills can only get us so far. We can look at these and say, they look pretty different, but we need to have a way of deciding. We need to know, is this difference big enough to be real? It's possible that this difference is just due to random noise, to error, that every time we draw a sample, the sample will be slightly different. And I'm sure that there are some of you out there who got much smaller differences between the means and some who got much bigger differences between the means. If 100 of us drew a sample and compared it, we'd expect there to be a lot of fluctuation. That random sampling error is going to mean that we would each draw different samples. We would each end up with a different estimate of what the age difference is between the men and the women. The other possible explanation is that the groups are actually truly, really different from each other. And so we need a way to decide. We need a decision rule. Let's think about our population and sampling a little bit more. So in this case, we're drawing this from a small population. There were 176 total actors and actresses in our population, and we're completely aware of the entire population. But often we're considering really different populations that are much harder to define, where we don't have a list of every member of the population. So if we are interested in human beings or even Americans, they're very large populations. There's not a list of them. We certainly aren't going to be able to gather data on the entire population. And so we draw a sample. No two samples will be identical. There'll be that random fluctuation, that error between the samples. That sampling error, we know about it. It's okay. We can estimate how much sampling error there is based on the variability in our sample. If you're recruiting participants for a study and you do know the entire population, then you could draw a random sample, a simple random sample. And then you would know that the individuals that are in your sample are representative of the population. And you'd know that the data would be a true estimate of the underlying population values. But even still, that sample won't come up with the same values every single time, and it won't be exactly like the population. If you'd gathered your sample on a different day or a different time, you'd have enrolled different individuals. The measurements would have been similar, but there would be differences. Just like these random samples that we've been drawing from populations. The measurements are similar, but they're different. Every sample is different from each other, even when they're drawn from the same population. So that difference we call random error, or we call sampling error. Just as a reminder of how we draw a random sample, the first thing we need to do is identify all the members of the population. And as we've said, for Academy Award winners, we do know all members of the population. We have a list of them. But what about other populations of interest? If I was interested in all UC Davis enrolled students, is there a list? Could I know the entire population? Sure, I could. The registrar's got a list of all of the enrolled students at UC Davis. How about if my population of interest was children of divorce in America? Is there a list of them? Would I be able to start with a list that listed every member of that population? No, I think that would be far more difficult to identify. We would be able to find children of divorce in America, but we wouldn't be able to find the entire list of them, and we wouldn't therefore be able to draw a random sample. The second step in drawing a random sample is to select that sample in such a way that every member has an equal chance of being selected. We've talked about flipping a coin or rolling a dice or pulling names out of a hat or using Excel's random number generator. Let's talk about that decision rule. Now that we understand that we want to make a decision, we need to touch on this concept of inferential statistics, particularly the t-test or a means comparison test. So what we're asking here is all about sampling. The question that we're asking is, when it comes to the age at which they won the Academy Award, are the men and the women samples drawn from the same population? Have I just drawn two samples from the same population here? Or are they samples drawn from different populations? We know that the means are going to be slightly different for the different samples, even if they were drawn from the same population. So the question is there a big enough difference for us to think that they're drawn from different populations? To make that statistical decision, we're going to compare the means. So it's going to be a means comparison. We're going to look at those means and compare them using subtraction. That's how we compare things, and you've already done that, right? We're going to compare those two means, and we're going to take into account the standard deviation in each of the groups. And so we're going to look at the distribution that is defined by this mean and standard deviation and the distribution that is defined by that mean and standard deviation, and ask the question about how much those overlap. How likely is it that those are two samples drawn from the same population, or if they're two samples drawn from two different populations? The calculation is a ratio. That means it's one number divided by another number, and it's called the student's T. And the formula is roughly this, that T equals the difference between the group means divided by the average difference or the variability within each group. So we're going to take the mean of group 1 and subtract the mean of group 2. And then we're going to kind of average this standard deviation of 9.9 and standard deviation of 6.9 and come up with a number that is an estimate of the variance within each group. Here are some questions to think about just when we're thinking about making this calculation. If the means of the two samples were pretty much the same, what would our ratio equal? Do you need a hint? So if the means are the same and you subtract one mean from the other as the top number of a fraction, you'd get 0 as the top number of a fraction. 0 divided by anything is going to be, right, 0. So if our t equals 0, we know that that means that the means were pretty much the same to begin with. The groups had very similar measures of central tendency. What about if there, in this case, is a 9-point difference between the means? So the top number on our ratio is going to be a 9. But what if the average standard deviation was also 9? So the bottom number on our ratio would also be 9. What's our t going to equal then? Right, it's going to be 1. Any number divided by itself is 1. Whether that number is 9 or whether it is 300. Imagine, you've got two samples. There's a difference of 300 between the means. That sounds huge. But if you say there's also 300 points variability within each group, oh, well then you've got one number divided by itself, 300 divided by 300, and that's also going to equal 1. So if t is close to 1, we're going to not think that these groups are particularly different. So once we've calculated the t ratio, we'll then decide if this ratio was likely due to chance, was it just due to sampling error, or is it due to a real difference? Is there probably a real difference between the groups? The way we make this decision is to find the probability of calculating a specific t ratio if the groups were actually the same. So as we were just saying, if the groups were actually the same, the samples will be slightly different, but the resulting t ratio is going to be close to 0 or at most around 1. We're very unlikely to calculate a t ratio of greater than 2 if the groups were actually two samples drawn from the same population. It's not unheard of, but it's going to be very rare. We're willing to decide that the groups are different if the probability of calculating that T ratio is less than 5% of the time. So we need to take some risk in our decision making, and we've decided, and this is pretty standard across the sciences, that a 5% chance of making a bad decision is something that we can live with. And you'll see that written as p less than 0.05. And what that's saying is the probability of calculating this T ratio, if these were two samples drawn from the same population, is less than 0.05. So the probability is less than 0.05. There's less than 5% probability that we calculated this T ratio from two samples drawn from the same population. That's all I'm going to talk about with the inferential statistics. You're going to take statistics classes that will talk to you more about the actual formulas and how you calculate those. For now, what I want you to hold on to is that if we have a large T, if it's bigger than about 2, then that likely means that there really is a real difference between our groups. And we can look at those and say the men and the women win this award at different ages. So if the probability of that difference being due to chance is less than 5%, we will claim that we found a real difference. There are great statistics calculating programs that will do all of these calculations for you. What you need to be able to do is know how to interpret them. So I've just put in the mean of 37.3 with a standard deviation of 9.9 and a mean of 46.3 with a standard deviation of 6.9. And that calculates to a T ratio of 3.73. I said that if it was close to 0 or close to 1, we'd be pretty sure that these were two samples drawn from the same population. 3.73 is nowhere near 0 or 1. It's huge. And so it is associated with a probability of less than 0.0003. So we are very confident in concluding that these are two samples drawn from different populations, that the underlying population of age of award of actresses and the underlying population of age and at award of actors are different from each other, that they've got different means, different measures of central tendency. Let's write that up. Let's add that to a narrative. So we're going to go ahead and start a Word document and start with a statement that compares the variable labels and end that statement with the inferential statistic. That's your evidence for being able to make that statement. And then go on to specify the exact difference. So here's maybe what I would say. I'm going to start with a statement that compares the variable labels. When it comes to the age at which actors and actresses win the Academy Award, there is a statistically significant difference between the genders. And then I'd end that sentence with the statistic that allows me to say that. And I've got that written down in APA format right here. And then I would interpret that. So I'd say, on average, females are awarded the Academy Award at a younger age, and I'd give the mean and the standard deviation to back that up, than the males. And I'd give the mean and the standard deviation to back that up. So when you're writing your interpretation, you make strong statements and you back it up with the statistics. Now, we said that the groups were different. If we have two numbers and we know that they are really different, we can just easily look at them and see which one's younger and which one's older. So knowing that there is a true difference, we can say actresses are younger when they win this award than actors. Let's prove to ourselves that two random samples drawn from the same population would look similar, would look more similar certainly than two samples drawn from different populations. So let's take another sample of the actresses. I'm going to highlight columns A and B and data sort by column B random because my list has headers, and click OK. And then here is my second group, my second sample. I'm going to go ahead and paste that over here into column I and label it as the second sample. Let me just make a copy of my first sample and paste it right here next to the second sample so that when we come to paste it over and to see it, it's all there and easy. All right, so I've got 2 samples from the population actresses. I wonder if they're going to look the same. Let's take a look at them. I'm going to highlight that data and copy it and jump to see it. Come down to the bottom left corner, add a data set. Control V to paste. I'm going to call this same population, just so that we remember what we're doing. First column is a label. No, I don't want to check that. The first column is data. And load that worksheet. Okay. Let me clear these. So I've got age at award by gender, and then I've got the data set, same population. All right, let's take a look at them. I'm going to drag that first sample into the graph. I'm going to click to add a new graph and drag my second sample in. Look how nice. See, it automatically puts them on the same scale for us. Let's look at those descriptive statistics. So let's look at a box plot with the standard deviation and the mean and apply to all. Wow, that's pretty convincingly similar, isn't it? This is a situation where the resulting means are almost identical. The top of our t-ratio is going to be tiny. It's going to be 0.1. The samples are different, but those means are really similar. When I plug these numbers into a statistics program, it returned a t-ratio of 0.033. Do you remember what we said about t-ratios that are close to 0 or close to 1? That means that they were drawn from the same population, that what we've got here is 2 samples drawn from the same population. We know that's true, but again, when we come across this pattern in other data, we will understand, we'll be able to use our visual reasoning skills and understand that these 2 samples are not different on this outcome measure. Let's practice writing up this result. We would, again, start with a statement that compares the variable labels, where we'd say maybe when it comes to the age at which these 2 samples of actresses won the Academy Award, there's no statistically significant difference. And we'd end that statement with the inferential statistic. That's our evidence of being able to make that statement. Then we go on to specify the exact difference. Now, we've got no significant difference here, or we call that a null result. We frame the narrative without making a strong conclusion. That is to say, you would write, there is no evidence that they are different. But you would not write, these groups are the same. I know, it's a subtle difference, but it is important. It's an important difference in that phrasing. Let's practice that again. When we have a null result, we would write, there's no evidence that these are different. We do not claim that these are exactly the same, or that the groups are the same. It's similar to in the judicial system why they conclude not guilty instead of concluding innocent. It's a similar sort of phrasing to that, where it's a subtle but important difference. So we might say, when it comes to the age at which these 2 samples of actresses won the Academy Award, there is no statistically significant difference, and then have our t-ratio. There is no evidence that the first sample, and we'd add the means and standard deviation, is different from the second sample and the mean and the standard deviation.